Well, there is 2 or 3 more results to finish this section about general multipliers, and then we switch to study more specific ones. Here is one of them. I mean, it's written as a corollary here, but I prefer to call it a proposition, or even a theorem. As before, H1 and H2 are KHS, 2 are KHS on X with, we don't need kernels here, but anyhow, I write it with kernels K1 and K2. And let F be a multiplier from H1 to H2. And then we have this beautiful property, and important indeed. Then MOF star, that joint, acting on KY2. 2 here means the kernel for the second space. So this acting, M star acting on this, gives us the kernel in the first space. Of course, with a constant Fy bar. And this is true for any y in the space, the set X. In particular, and that's the particular case that we usually use, when the 2 spaces coincide, I mean, H1 equal to H2 equal to say H and K1, K2, K. Then every kernel function is an eigenvalue. Eigenfunction, sorry. Eigenfunction of MF star with, well, eigenvalue I will write more explicitly here. MF star acting on KY gives us back KY with eigenvalue Fy. And we will see a consequence of this momentarily, but first let's prove it. The proof is very straightforward. It's not difficult. For any H in the first space H1, what can we say about, well, let's start with F of Y, H of Y. I calculate it into 2 methods. First, well, it's F of Y, and H is H scalar product KY1 in the space H1. And I can take this inside. That's one way. The other way is to write it as fh evaluated at point y, or the same thing as m of fh evaluated at point y. And note that mfh is in the second space. Evaluation at point y is equivalent to inner product of this function with the kernel, but the kernel in the second space. And now I take mf as an operator to the other side. So this becomes h, mf star of ky2 in h1. And now compare this one with this one. For any h, these two are equal. So for any h and for any y, well, y is fixed. I don't need to mention that. H fy bar ky1 in h1 is equal to h mf star ky2. Immediately we obtain what we were looking for. mf star acting on ky2 gives us ky1 with scalar fy bar. So that's the end of the proof. I go back to the special case that we saw above. H1 is equal to H2 equal to H. In this case, we saw that mf star ky is equal to fy bar ky. And if we take the norm of the both sides, I start from the right side. So it gives us absolute value of f of y times the norm of ky is equal to the norm of mf star ky less than or equal to the norm of mf star norm of ky. So if y is such that ky, its norm or itself is not equal to 0, it's the same thing indeed, then we conclude that f of y is majorized. And let me add one more thing. The norm of t star is equal to the norm of t. This is majorized by the norm of f. And this is also true if k of y is equal to 0, because in this case, f of y is 0. So, let me write it the way it's written in the book. In the book, it's written just this part. But if k of y is in many function spaces, the multiplier is a subset of the space because the constant functions are in this space. And in that case, if k of y is 0, f of y is 0, and this is automatically true. But let's stay with the, kind of general setting and not assume that the constant is there. So here is the conclusion. F of y is majorized by a constant MO. I hesitate to write it in this way, even though it's written in this book and in many other places, because when we write norm infinity, usually a measure is involved, but here it's for all y. So we don't need to think about the measure. Instead of this, I prefer to write for all y in the space X, f of y is less than or equal to the normal f. And again, why I write for all y, because the spaces we consider, like Hardy, Dirichlet, Bergman, and this is always the case, k of y is not equal to 0. So conclusion is that a multiplier is a bounded function, but the converse is not true, and we will see that's the topic of, the concluding topic of a course. One more observation.
Sir,
Yeah.
we proved that if k of y is not 0 for all y, then f will be bounded.
Yes.
Um,
As I
Let
said.
me ask you in this way that if the kernel function is continuous,
Yes.
can we say something about the multiplier functions? Will they become continuous?
If the kernel function is continuous, can we see the multiplier?
Continuous functions and X is a topological space. Then
I haven't seen this theorem in the book, but it has to be true. I tell you why. You remember we had a theorem, kind of at the beginning, just before Moore's theorem, that if the kernel is continuous, then every element of the space is also continuous.
yes, right.
So if you have such a kernel, and then you multiply, say, f by kx, this has to be continuous. The product is continuous because in the space, and this element also by itself is continuous. The only problem is that is it equal to 0 or not? And as I said, the same difficulty I had here. In most of the spaces that we consider, k of y is not 0. And that is why we can say that, yes, the kernel is continuous, because we can even locally divide by kx and say that f is continuous. However, if your space is such that at a point x0, kx0 is equal to 0, then you cannot say so. Why? Because consider any multiplier. So pick any multiplier. Say f. And then define g to be equal to f of x if x not equal to x0. And at point x0, whatever you wish, you have absolute freedom here. It really doesn't matter. G is still a multiplier because for any h in this space h at point x0 is equal to 0. And therefore, gh is the same as fh. This is for all x. If x is not equal to 0, they are the same. And if x is equal to x0, then this is 0. So still identity holds. So this means that g is also a multiplier. But you have absolutely freedom here in the definition of G at point x0. You can define it such that G is not continuous. So the only obstacle is kind of artificial case. I mean,
but if kernel is such that ky is not 0 for all y,
then it is continuous, yeah, for sure.
why it is continuous?
And unbounded, continuous and bounded, yes. I mean, because I explained here, because the product is continuous, it's an element of the space, and kx by itself is continuous, non-zero. You do the division. True? So you obtain something continuous. So it's a consequence of the theorem that we had before, even though it's not explicitly mentioned in the book.
Can I suggest another proof of that inequality? Absolute value of f of y is less than or equal to the normal multiplication by f, that one there at the bottom. There, yes. Okay, let's assume ky is not 0, which means there's some function in the reproducing kernel Hilbert space that's not 0 at that point.
Yes.
Look at the operator of multiplication, fix y. Look at the operator of multiplication by f minus f of y.
Okay.
That operator is not surjective because every function in the range is 0 at y.
True.
Therefore, f of y is in the spectrum of multiplication by f. And therefore, every element of the spectrum has absolute value less than the norm.
Yes.
So you don't need to go through the adjoint that way.
That's true. Very beautiful indeed. I mean, thank you, Sheldon. Yeah, it's a very nice observation, which I mean, I didn't notice before. Thanks a lot. The last item in this section is about Bresin transform, which indeed, I mean, I don't know if Sheldon, you have the nice paper you wrote, I mean, indeed many years ago about Bresin transform and its application. If you have, you may share, but I mean, the thing I do here, it's very elementary, just definition and one property.
I'll look for it, see if I can find the electronic copy.
It was free on internet.
Okay.
Yeah. So here is a definition. I mean, as about H is an RKHS with kernel K, and T is a bounded operator on H, B of H. The Bresin transform BT at point Y is defined to be TKY in a product KY and normalized. And of course, we have the same difficulty as before. We have assumed that KY is not equal to 0. So it's defined at the point that KY is not 0. And this is called the Bresin. The motivation for this, the way explained here in the book, is that if you have a multiplier f, then what can you say about MF KY? Well, as we did about, we can transfer it to the other side to obtain the adjoint, and then this becomes F this means that I'm already tired. This is not a good sign. Ky, ky, here, ky. This is f of y bar ky, and f of y comes out, and ky inner product ky stays. And if we divide both sides by this, assuming again it's not zero, we obtain mf ky divided by ky is f of y, is a method to calculate the multiplier using this combination. And this is precisely the Bresin transform of the operator mf. So this is b mf at point y. The way we define that's the motivation for the definition. And the simple property, I mean, there are many interesting properties, and if Sheldon succeeds to find his own paper, you will see many interesting results in that paper too. The one I want to show here is the fact that the multiplier algebra is closed under a specific topology. On B of H, we have at least 3 topologies. The first one is the norm topology. And the second one is, it's called a strong operator topology. And I explain it this way: Tn converges to TSOT. That's the definition if and only if for every element of this space H, Tn of f goes to T of f. And the last one is weak operator topology. This is over here. And in this case, Tn goes to T weak operator topology if for every f and g in H, Tn f scalar product with g converges to T, f, and g. I mean, the name explained, I mean, the norm topology is the strongest one, and then in the middle we have SOT, and the weakest one is the weak operator topology. The good thing about weak operator topology is that I leave it as an exercise for you. It's a very simple exercise that if Tn goes to T weak operator topology, then the adjoint does the same. I mean, just take Tn to the other side. This is very trivial, I mean, simple to prove. And I will use it even in the theorem. Yeah. So, mentioning the theorem, the last theorem of this section for the book, H is an RKHS on X, then mult H, the set of all operators. We need to be, that's not a good notation. This is precisely the thing I wanted to say. Don't fall into this mistake. Mult H is used for the function. So it's not a good notation here. The MF is the set of operators. MF, the set of operators, is such that F is in mult H. this is a unital subalgebra of B of H. Up to here, it's we already know that. New part, that is closed in the weak operator topology. That's the new part of it. So 2 ingredients, a unital subalgebra, we know that, but the closeness in the WT, this is what we want to do. Well, the way we do it, to show the closeness, we consider MF lambda, not necessarily a sequence, it's a net, generally speaking. It's a net of multipliers. And we assume that this net of multipliers, MF lambda, converges in weak operator topology to T, which is a bounded operator on H. And our goal is to show that T is also of the form, say, MF, where F is in mult of H. This is what we want to show. So we need a candidate for for F, but the candidate can be seen here in the motivation, in the definition of B. When we do the Bresin transform of the multiplier, we obtain f of y. So if we apply these to f lambda, for sure, we know that. So we know that. Bresin transform of the operator mf lambda. It's a horrible notation, but I'm sorry for that. We have to live with this. We know that this is f lambda at 0.1. And well, based on the convergence, a good candidate, we define f at point lambda to be the limit over lambda of f lambda y whenever the limit exists. We don't know yet, but we will see where it exists. And let me see for a moment. Yeah, when say, let me erase this. It's a part of the proof that we show that this limit we show this exists, and this goes to BT. So our definition is like this: f of y we define to be the Bresin transform of T at point y whenever ky is not equal to 0. And 0 if is equal to 0. Then let's see what we can say about f of y, and if we can show that f is a multiple. Now the goal is to show that f is a multiplier. But here, the way we do it, for any x and y in x, t applied on x is a function. We evaluate this function at point y. Well, it's t kx in a product with ky. And taking a joint t star ky. We saw about that if a net converges weak star operator topology, then the same is for the joint. So this is equal to the lim over lambda kx, and here m f lambda star ky. This is by assumption. And now we use the fact that by previous results, that this is an eigenfunction. So it's f lambda y bar ky, and we can take f lambda y kx ky lim over lambda f lambda y kx at point y. So as we see that if kx is not equal to 0, this also implies that the lim over lambda f lambda y exists. Let's see what is in the chat. Oh, okay, it's the paper. Thank you, Sheldon. And also, I mean, compare t x on kx evaluated at point 1, t kx evaluated at point y is equal to f of y, that was the definition, acting on kx at point y. Another way to write, this is true for any y, the same thing to write this identity is that t kx is equal to f times f kx. That's almost the definition, and almost the definition of a multiplier. Almost, because not every function is there. We just have the kernel functions. For kernel functions, f acts as a multiplier. But now we use the fact that t is a bounded operator. For any h in the space h1, there is a linear combination of these multipliers which are close to f. There is, I mean, we can call it hn. There is hn, which is in a span of kx, x in x, such that they are close. I mean, norm of h minus hn is as small as you wish. For example, less than 1 over n. And since this is in a span, we know that THN is equal to FHN because of this span. And now what can we say about TH? TH minus FH, that's the usual trick that we do in analysis. Is equal to TH minus THN plus THN minus FHN plus FHN minus FH. And now take the absolute value, and here we use, this is equal to 0, this part. And here we use the fact that T is bounded. And the last one is also small, thanks to this one. And therefore, we conclude that TH minus FH, indeed, it's independent of N, is we can say that this goes to 0 or eventually is equal to 0. It's a limiting process, which means that F is a multiplier. Or T is equal to MF, and we are done. I was a bit not so exact here, but you understand what I mean. I mean, that's the usual trick that we do. In analysis. Nothing more in this last section, and this finishes the chapter 5. After the break, I want to talk a little bit about the special cases like Hardy spaces and more about Dirichlet spaces, what we know about the multipliers of Dirichlet spaces. And that finishes our course. But before the break, Sheldon, do you want to talk a little bit about those two papers?
Well, I put 2 papers in the chat box about the Berzin transform. These focus on the Berzin transform on the Bergman space, or one of our key examples of a reproducing kernel Hilbert space. And the idea is that if you have an operator such that T of the whose Berzin transform goes to 0 at the boundary, then you want to know whether that's equivalent to being compact or not. So one direction is easy, that if the operator is compact, then the Berzin transform going to 0 at the boundary is true. But the converse is not true for all operators. So this shows that it is true, though, for nice operators. It's true for anything in the norm closed algebra generated by the tuplets operators. So you really see how useful the Berzin transform can be by looking at that.
Okay, thanks a lot. I've looked at the one about the Berzin transform on the Bergman space before. I mean, even quite recently on that. Very, very interesting article. And thank you for sharing them.
Thank you.
Just before the break, I mean, let me see if I can go a little bit up here. Well, it doesn't work. Here, the way in the book is explained. I mean, I wrote it like this, and I mean, just out of my mind. But the way it's written in the book, it's by evaluation. I mean, evaluated TH at point Y and did the limiting process based on HN to show that it's equal to f of y, h of y, and so the same conclusion. This is more straightforward, which is explained in the book, but I believe this one can be made precise too. But I mean, let's do it the way the book is done. So, well, this finishes this part, and we have another break, and we come back to talk about more about Dirichlet spaces.